Okay, you can start whenever.
Cool. So first of all, thanks a lot for inviting us. It's a super exciting opportunity to be here with all the big names of violin acoustics. It's something completely unexpected for me, and you will see why. Second, I don't have a group. I'm just doing a postdoc here. Just started last year in November, then COVID came. I went back to Chile for a few months. But I've been working with Davide, who is making his master degree thesis. He's also a mandolin player, and we studied by means of simulations, the violin. And Daniel, who was actually my ex-boss in Chile when I was doing data science. We are friends from the university, so he really liked what we were doing with the artificial intelligence predictions. So he said like, okay, let's work together. And I'm doing the organization and the trumpet also, but I don't have a picture of me. So why am I here today? And this is a bit of weird slide to present or like weird thing to say, but for me doing violin research, it's a very personal matter because I was finishing my PhD in physics in Holland, in the Netherlands, when I met my first ex-wife, and she was a German girl, and one day she took me to her family house. And I had heard that they were violin makers, but I mean, I come from Chile. We don't have a very good tradition of crafts or anything handmade or actually quality. We just sell rocks mainly to China in the form of copper sulfate or something. So when she took me to this little town in the north of Germany, in Celle, it's between Hanover and Hamburg, I entered like a workshop that looked a bit like this. And the smell of propolis and sandarak, it just like killed me. It was such a like sensual world. Compared to like my PhD in physics, which was computer simulations of little spheres that were colliding, all very dry. So I kind of started to leave physics slowly but surely to make a workshop. I moved back to Chile, where with some friends, we created this taller porteño, we call it, like, because Valparaiso is a harbor, a port. So, and it's also the cradle of all the music and culture in Chile. And in this place, I created a hand tool workshop mostly, very Japanese inspired, as you can see by the sauce. Till one day, I decided to go on vacation to Cremona for the Mondo Musica. And I had the whole weekend of Mondo Musica and Monday, even though the museum was closed, I came to see it. And I realized there is this lab here. And I just knocked the door and say like, hi, I'm Sebastian, I'm a physicist and luthier. Can you do a tour for me of the place? They showed me around and I was like, oh my Jesus Christ, this is the place I want to come. So a year passed, I talked with Augusto, I sent him a mail. We got on talking and long story short, a year after I'm here. But something that was very clear from the beginning is that I was far too old to start making violins at 30. Actually, this is my first violin. It's still halfway. I think I started in February, but yeah, I stayed in Germany while I was in Chile. And the Stradivarius had a big advantage with me, and the pure numbers were clearly a drawback for me. So even though this research is just like 1 year on the making, I've been thinking about it for 7 years. Since I started like learning about what violin making is, I started thinking how to, with my physicist mind, how to study it. It seems like I somehow like got into it myself. The approach like I developed, it's quite different. And I think it's going to be a bit weird. That's one thing. And also maybe, I don't know. I hope you find that at least interesting. So like the first thing we did, like to get to know like the tools we had and the things we could do, it was like kind of simple optimization and plate creation from the 3D scans that we have here. The starting point, it's the Messiah that was for, I think, a day here, and the Cremona lab managed to get a scan. And the nice thing of the Messiah is that, as you all know, it's in pristine condition. So we can have a very, like almost primordial shape of a violin from it. But using the scans, they have too many points and they're slightly noisy, even though the Messiah, it's quite in new condition. So what we do, and with the idea of creating thousands of violin, it's to parameterize the surface. And this can be done for both the top and the bottom. In this case, it's the top. And what we use is just simple 4-order polynomials that whose coefficient vary from tail to the neck of the violin. The coefficients in the Messiah are very beautiful. The scan is also very good. So we have a very smooth curve. We also have data for the Cremonese, for example, in which the varnish, it makes a very noisy scan. So this looks horrible. And we have some methods for smoothing the surface. This is a contour plot of the outside height. And as you know, we cannot open the Messiah and measure the thickness. So one of the problems we had was to, maybe a note here, you can see that our top, it's completely symmetric by construction. The errors under the fingerboard are eliminated. These are scan errors because you cannot get with the scan. Actually, I could show if I turn around my computer, but maybe after. So what do? It's in the inside, we find different zones, which can be modify their thickness in an independent manner. On top of that, we put a homogenizing algorithm that makes very nice violin-like inside curves. In the literature, I found there was something similar of optimization of the arching, but it was done with maybe like 12 points in the arching, and they will vary in a very discontinuous way, which to me, like with the little I know of violin maker, it's very unreasonable. Like nobody will want a surface that is bumpy on the top. So our way of creating the inside, it's ensures that it's a smooth contour. And also it's in line what the Cremonese makers used to do. In particular, you can see that the F holes have always a different density, well, not always, but they have a different density that it's mostly symmetric. And you can see maybe in the lower boats and the upper boats, some regions of thinning of the plates. So what we do, it's like pretty much what everything does, what everybody does, it's to look at the modes 1, 2, and 5. And actually, we just look at the frequencies of these modes, not at the spatial distribution of them. Sorry. In particular, to the ratio of F5 to F2. And this is just an example. I mean, we can move the 8 parameters, but since it's a bit more difficult to visualize, we're just moving the upper boats together. I mean, upper boats independently, lower boats independently, but as a one big piece of material. And we can plot the 2-dimensional axis. And what this illustrates is the fact that the dependence of vibratory observables on the variables, it's not linear. If it's not linear, you cannot analyze them independent. So you need to go for some more complex way of analyzing. One of those is we do a pseudo Monte Carlo steepest descent minimization, where we can define a loss function, for example, the distance between the ratio of f5 to f2 to a given number. In this case, for the case I, it's 2.3, which was in line with some paper we found from Curtis, if I'm not mistaken. And another loss function, because this is kind of loss function agnostic, can be the spread of the modes in the frequency domain. If we had an equal temperament piano, the standard deviation of this will be 0. To minimize, we cannot go to 0 in a violin, but we find that different thickness give different vibrational responses.
Sorry, Sebastian, may I interrupt?
Yes, please.
What do you want to optimize?
The ratio of f5 to f2.
And why? For which purpose?
It's historically, we found this paper that shows that historically Cremonese makers are in the range of Colin also said it, but his number was 2.15 plus minus 0.15. The paper we are referencing, it says it's 2.35. And one of the hypotheses is that this ratio somehow has implies that the sound is good. But in
and you optimize what? The thickness of the plates?
Yes, I vary the thickness of the plates in each of the 8 regions to get as close as this as possible. The result is that we are 2.301. It's very close. Meaning that, and I will come back later to it, but what we can do if we knew what is a sweet spot for violin top plates, or what the luthier wants to obtain, we could tell them how to carve the plates to obtain that number. Okay. As Augusto said, we're more interested in the tools than in the actual results, because I will say later that this is arching and outline dependent, so it's not very generalizable, but the idea is that we have a method for the optimization of the thickness profile.
So you are fixing the arching?
We are fixing the arching. We are starting with the Stradivarius Messiah arching.
Okay.
Any other questions? If I'm going too fast, just please tell me. Somebody's typing, I think. I can't see the chat though, so.
Jessica, you can ask, instead of typing.
Can I ask for a bit more explanation of loss function B? So it's
yes.
It's the cost function used in an optimization algorithm. But what exactly does Fi over Fi minus 1 mean?
It's the standard deviation of the ratio between consecutive modes. Like if we think of
spacing.
Equal, yeah. If we think of a equal temperament piano, the ratio between each note, it's always the same. Yeah. So it was just a random. I mean, it's not so random. There is a guy in California doing guitars, and he does a lot of FEM simulations, optimization, and he has this sentence of saying that he looks for a homogeneous spreading of the frequencies in the frequency domain. So that's what we wanted to look at.
Okay.
But it could be anything, eh? Okay. Yeah, sorry, I cannot see a chat, so if there is something going on. Another thing we did, because, okay, yeah, the top plate, it's just one part. We also have the bass bar and the F-holes. We look also at them. It's the fact that historically we had a change in the length of the busbar from the Baroque period to the modern period.
I'll have that one.
Many, many thanks. Okay. I'm going to meet Ness there at 2:30.
Oh, great. Give him a love.
Sorry, I'm hearing calling.
Yeah, I turned off his microphone. It's okay.
Yeah, thanks. So one question was like, what's the influence of the length of the busbar, for example, related with another parameter? Because we saw already that nonlinear interactions imply that you cannot look at one. We modify all of them, but these two were the ones that changed most the ratio F5 to F2. And you have that if the length of the busbar grows, as well as the angle, the orientation of the angle, you have the same frequency response. So in this way, you have two parameters that you can modify together to obtain the same behavior. And these like contour lines are iso lines of a certain frequency response. So as long as we move, let's say, between the blue and the green and the yellow, we can vary both parameters and we're going to obtain the same response in this particular observable. Other observables would vary in a completely different way. But also tell us that if we move like this in this two-dimensional space, we're not going to see any change. Whereas if we move along this direction, that it's making the bar longer and increasing the angle, we are going to see the most variation. And the best way to see this is with principal component analysis, and I will come back to this later. Oh, I have to hurry up. Okay, why the
sorry, Sebastian, there are a few questions. So first, the F5 and F2, that's just F5 and F2 of the top, or the top and the backs, top over backs?
It's only of the top without the busbar and without the F-host. It's just the free plate.
Okay, so it's just a free top plate. So optimization is only on the
free top
plate without base bar and without F-host. Okay. And the question was about what did you use for the mechanical characteristics of the plate?
Well, yeah, that's a great question, because we just took one particular set of parameters from like Engelmann spruce. Why? Because we've seen that the material parameters just change the absolute value of the frequencies in like a reasonable range, not the relationship between them. So we look at just one. But yes, in the future, we're gonna, and I'm going to come back to this, like we need a big vector with all the characteristics, like geometric, material, etc., etc., etc. It's coming. Why 2.4? This is like a question always. We don't know. But what happens when you do the F-host and the busbar? The modes will change. When you cut the F-host, the plate becomes a bit more soft. So the eigenmodes go down, all of them, in a particular way each. And when you put the busbar again, you make them stiffer again. So the modes go up in frequency. And we go that from 2.4, you go to 2.05. That was another topic. It's slightly different from the one of 2.3. But you can have like different thickness given different F5 to F2 values. So, and I already announced this. We vary, like the good thing of having a parametric top is that we can easily varying the parameters of these coefficients. We can change the arching, say, from a Guarnieri to a Stradivarius. And if we change like 1 millimeter the top height of the arching, we obtain qualitative different results. The same for the outline. So more than like I found a very like a simple model of tuning plates. That it was an Excel file that gives you the frequency and where to carve. You cannot, I think, do that. It's very dependent on the geometry, in the particular geometry that you're working with, and also probably in the material. And that's why if the Cremonese Masters did something like this, they knew each particular piece of wood very well. Okay, so that's the first part of this. And the chapter 2, it's artificial intelligence. Again, I mean, going back in my life history, I used to play Go. Actually, that's where I met Daniel, playing Go in the university. Go, it's a board game from China. I mean, it's 5,000 years old, so the names don't make much sense. But from that region, the oldest recorded game in the world. And it's very simple, it has 3 rules. And it was for years the benchmark for artificial intelligence. And computer programs could not go beyond like a person with a few months of experience playing Go. It's because the number of possibilities of each move is so big that you cannot compute it. Till one day when like nobody was expecting it, Google came with this AlphaGo program, and they challenged the best player in the world. And the machine won for 3-2, or 4-1, sorry. And one of the amazing things that happened, I mean, despite the fact of winning, it was that in one move, the computer did something that was completely ununderstandable for the human mind. Like players thought it was a mistake. And somehow the machine taught the humans like new possibilities of Go, which for me like, rings really attractive in terms of violin making. Okay, so going back to my personal fight with Stradivarius and how to compensate for 20 years of experience, we can simulate a lot of violins. That's something we can do, and that's the idea of artificial intelligence. You just like need a lot of data. But to do this, we need a way to parameterize a violin, which it's very, I think it's very similar to what Ramin was his name? The French guy from day one. I don't know if he's here. But Roman, thanks. So to parameterize, like this was, when I arrived here, like that was my first question. And we didn't have an answer for 4 months. But when actually I was standing like, on top of the answer. This is a picture from a Stradivarius workshop. It's in the collection here in the museum. And you can see that he builds the violins with circular sections. And nicely, for example, for the corners, the circles start in the same radius that the waist circle. So I just copied that. There are some numbers, so I put the same numbers in the computer and created these different points, like done in an iterative manner. So you define P6 in function of P5, P5 in function of P4, and all in function of P0, maintaining the continuity of the line. That's very important to reduce the number of parameters. And finally, we come that with 11 circles, we can define the outline of a violin, which fit very nicely historical examples that we have. The arching, how do we do it? We have 2. Like first, it's the longitudinal arching, for which we just took a 6th order approximation to the Messiah. Why? Because I just wanted to see the importance of the outline on this study. But we can also vary it and like add to this big vector of definition of a violin. For the longitudinal, for the transversal arching, that's this direction. What we do, since they are all different, we cannot define one curve. So we defined a functional form that fulfills the boundary conditions of the outline. That is along the y-axis. For each point, we have a fourth order polynomial that in the highest point, it's the longitudinal arching. In the borders of the given outline, it's 0 as well as its derivative. And that's why it doesn't fit well the Messiah in the middle, because it's functional. But in that way, we can just create, sorry.
Sorry, go back one slide. What the graphs, what are they?
That's the arching profiles for the...
A different cross section?
In this direction, yeah, the transversal. Okay. So for each point we have, and the idea is that it fits in the middle point and at the edges, and on top of that, the derivative is 0. That it's like, it goes nicely smooth in the edge. And they look like this. Sorry. It's a bit slow. It's very smooth, parametric. The definition we can have is as precise as we want, since it's just parametric. It just each mesh is around 5 megabytes, I think, if I'm not mistaken. David probably can add in the chat how much they weigh, and we can get from that the outline, the ribs, and the arching also, if people is interested in, because you can put this directly into a CNC, for example, which is our plan for doing experiments later on. But yeah, once you have a big data set of, something I didn't say, and I'm going to go back, sorry. We have these 20 parameters. So what we do is that we vary each of them with a Gaussian distribution. A Gaussian distribution centered on this particular outline that's similar to a Strad. And in this way, we have a big cloud of points in a 20-dimensional space that represents different solids, which are this one. And we put, for each of these shells, we compute the eigenmodes, and the first, we're actually looking at the 10 first frequency. Here is just the first 5 plot, and we put them in a neural network. And I like to see the faces that people have here, because I don't know if I'm speaking Chinese. Looks like a bit. The neural network, what it does, it's take the geometrical parameters, does some weird computations inside in a hidden layer of neurons, and gives you an output of frequencies. And you can see in the graph plot on the right that the ground truth, the actual value versus the predicted value, are very accurate. This means that we do not need to do finite element modeling. We just need to put the geometric parameters into the network, and the network tells us what are the frequencies with a very low error. So what can we use this artificial intelligence for? Which you also can call just like a matrix or a weird function. We can do optimization, the same optimization we did in the first part with the thickness profile, but in this time with the outline. Oh, I forgot to say that in this case, the thickness of the plates is constant always. And the question we asked was, if we start from the outline that looks like the Messiah. What are the outlines that give me a given frequency response? So for each one of these frequency response that go from, sorry, I didn't put it, it's 2.2 to 2.5. We compute with the neural network, and the nice thing of the neural network is that it's almost a differentiable operator. So it's very fast. It takes less than a second to optimize with 100 steps, which correspond to 100 simulations. And we get that if we vary the ratio F5 to F2, the solutions in terms of outline for this are increasing the outline, which we found super interesting. And the fact that somehow like the Strad is close to the green line over there, and it's very close to a constant thickness top that gives you the famous 2.4 number. And this is something that I really like from the physics community in artificial intelligence, is the fact that nobody is very comfortable with a black box. We all want to know what's inside, and this is called explainable AI. Are there any questions in the chat? Because I see like the numbers growing up.
There are questions, and Fabio is answering them in real time. So.
Ah, perfect. I got support.
Sorry.
Okay, so and this is where like Daniel's expertise, it's on doing precisely this. It's called black box, white box modeling. From like something that we really don't understand, which is the neural network, we can study what kind of correlations, mutual information, or other type of relations there are between the parameters and the frequency of the modes. And rather incredible, our 20 parameters correlate very nicely with particular modes. So parameter 1 and 2, which I will show you which are in a second, correlate with modes 1 to 10, except mode 5, which correlates a lot with parameter 14 and 16. And in 20, it's a bit also doing some things there. So these are the influence of moving each of the parameters. So parameter 1, which is the first radius of it's the position of the first circle of the violin, which essentially determines the distance to here. So it determines the width of the violin. But when you modify it, you don't only move like the waist, you move the corners, you move everything a bit. Parameter 2 moves in the other direction, so it makes the violin smaller. And parameter 14 may, I don't know if surprising or not surprising. I will let you decide that. Parameter 14 and 16, which are, sorry, I want to move the zoom view because I don't see anything. Perfect. Parameter 14 and 16 move the lower bout mostly, and the lower corner in different directions. I just put the half of the violin outline because they are symmetric. From the correlation, we can see that not all the parameters correlate with the modes, but only a few. And this is the only equation in the talk. It's the fact that since we have a prediction model which has 20 parameters, we can change one parameter for another in the model and see how well the system predicts. That gives us an idea of the importance of each parameter. The result is that actually the first two in order of importance parameter like account for most of the variability of the data. And with essentially 7 parameters, you can predict quite well a violin, the violin vibration modes. Why? And this is maybe a bit controversial, but I wanted to put it anyway, because the modes are not independent. When we talk of different modes, you know, like A0, B, C, whatever, they correlate with each other. In this case, this is a correlation plot, like I just simulated 10,000 or so rectangular plates. I mean, not simulate because the solution is analytical. But if you plot the correlation of the modes for a rectangular plate with different sizes, you realize modes are going from 1 till 20, I think it is, in both directions, down. The first mode has a lot of spread, a lot of variability, but the second mode has less. And as we approach the higher modes, they are actually all correlated to each other. So somebody said here, like there is, the modes are more and more complex as the frequency increase. When, I mean, I understand that that means like the spatial characteristic of the mode becomes more variable, but as the frequencies increases, the vibration only see the local material. Therefore, the frequency it's more and more correlated and becomes more and more simple to predict. So that was for a rectangular plate. In this case is for the violin plate. And we see that modes 1 and 4 are extremely correlated and they make a little cluster. Also modes 2 and 3. And mode 5, it's extremely different from all the others. So
Sebastian?
somehow we are, yes.
Yes, sorry, I'm totally confused because by definition, modes are supposed to be normal and like independent. But what do you mean by correlated?
You compute the modes, the frequencies of the mode, and you compute the cross correlation between any two of them. And yes, they are uncorrelated for.
Sorry, what are you correlating? The mode shape or the frequency or some other parameter?
No, the frequency. Only the frequency. I'm just looking at the frequency. Yes. So that's where the more complex and complex, it's in the space domain, but in the time domain, or in the frequency domain, they become more and more simple. And you can predict the next one knowing the previous one. Because, I mean, the shorter the scale you are looking at, the more like the modes don't see any of the boundary condition. They just look at the material properties of the surface where they are vibrating.
But so, and what are we looking on this slide? What is along the x-axis? What is along the y-axis?
It's these are scatter plots for each of the modes from 1 to 20 and the cross correlation between them, which is like just the scatter plot one and the other in frequency, yes.
And so the bigger, wider it is,
the bigger the spread, the more independent they are. And as you see, as we increase the frequency, independent.
The more what? They are independent if it's a line?
No. If they're in a line, they are completely correlated. If they are spread, they are independent. So the first mode, it's the most independent with the rest of all of them. because the first mode is the one that takes the dimension of the plate. And I'm varying that.
Okay, Andrew would like to ask a question about this.
Hi, I assume this correlation in the upper frequencies has to do with the crossover point when the plate goes supersonic and when it becomes a tweeter. So then the modes are related to the material itself rather than the construction. The modes become smaller, so they relate to one another because it's just dependent on the material, not on the shape, not on the graduation. Well, yeah, I understand it.
Yeah, but I mean, this is for just like a rectangular plate for which the solution is analytical, and it was not the clearest of the plot. But this is for the actual violin plates. And in this case, we find that even the low modes are correlated. Because, I mean, after all, we are simulating things that look like violins, so they are gonna correlate in somehow. I mean, that there is correlation doesn't mean that we know which way they are like functionally dependent between one and the other. Okay, we just know that they vary together. And interestingly, in the mode 5, there are a small cluster, like in the lower region for like the second picture of the mode 5, which we have no idea what it means. Okay, so, and I mean, one complaint that I hope it's there in the chat, it's that how can we use this for our violins? Because I don't think anybody of the luthiers here are making violins with these 20 parameters like we copy from Stradivarius. So an answer for that, it's, I have some water. An answer for that is that the outline has also information of the, okay, I don't want to say it has information of the parameters, but the outline, if you discretize like a lot of points, we actually did it with 720 points for half an outline, also has information, and you can compute the principal components of the outline. And the principal components are the direction for a given set of data where most of the variance is explained. So we can do this with historical violins. We can do this with our synthetic violins. And we have that actually the fourth PCA vector, it somehow looks like the first parameter in the sense that it reduces the waste. Actually, the sign is the other way around, right? It's a second. But the way in which modifies the lower bound, it's completely weird. The second mode, one could describe it as lowering the corners a bit, but at the same time, you have to move the bounds. The third one is making more tight the waist. And the fourth, it's a different movement of the corners and the bounds consequently. But this is just like data-driven figures, like nothing that we can like somehow like explain it, because it has to do with the variance, like intrinsic property of the data set. And we can do the same analysis that we did like between the modes and themselves, or the modes and the parameters, and it's to look at how the PCA vectors sort by variance correlate to the modes. And we found again, sorry because this picture is the other way around in the y-axis, that the first mode of the PCA correlates a lot with the first 10 modes except of the 5, and the 5 correlates with other direction. This means that, I mean, if you try to see it in 2D, it's horrible, maybe this. You have one direction that determines all the modes from 1 to 10, and another orthogonal direction where you change mode 5. Therefore, you can change the ratio F2 to F5 just by moving in this direction that only moves mode 5. And again, the frequency of mode 5. And since we have the PCAs and we have the outlines, we can also do, it is called a reduced dimensionality prediction. What we do, instead of taking all the parameters that you saw, that the R square, like the closest to 1 the R square is, the better the prediction is. For PCA with 10 components, we have an R square of 9, so it's the blue points here, where if we just use only the 6 first parameter, we lower the precision of the prediction in the neural network. Okay, so that was the artificial intelligence, and I still have some time, that's great. Before continuing, I just want to say that one of the things we need to add to this, it's like, I mean, we're looking just at the outline, but in a parametric manner. We can change the arching, we can change the thickness profile, we can change everything and just keep on adding input variables to the network. And our idea is it will predict as well. And somehow related to this, but also on the other hand, slightly orthogonal, it's the mapping of historical violins. And this is the idea. Like, it's difficult to talk about how similar or how different two violins are, you know? And I think we would like to have Google Maps that tells us, like, how do I go from Guarnieri to Stradivarius? In Cremona, I think it happens to be that they are straight, so you can actually walk them. But in violin making, we're moving in a, I don't know, 100-dimensional space. So the shortest path is quite difficult to compute. So what did I do? Since we have the scan, we can compute the outline very accurately. And we have in the collection of the museum, some, like, I think 12 violins, of which 10 are very good scan, and we can compute the corner position very accurately. Together with the corner position, we can compute these distances and plot them here as features. We call them, that's the standard artificial intelligence name, where you subtract the mean of a data set and divide by the variance. So they are all standardized and they all have mean 0 and standard deviation 1, which is somehow a genetic code for the violin outline. And as long as you define enough independent dimensions to measure difference, you are good to go. We know that 20 define a violin pretty well, the outline of the violin. So how does these 10 like simple features that like you can measure in your own violins in the workshop with just a ruler? We compute the Euclidean 10-dimensional distance between them, and you can compute the distance of one with the other and of other with one, and you have this matrix, which now it's not a correlation matrix, but it's a distance matrix in the 10-dimensional space. And we have that Stradivarius, that's yes, and Guarnieri. Clearly, the 3 Guarnieris made in the same year are pretty much a copy of each other. So their distance is very small. Whereas for Strad, we have like a much greater evolution in time. And we have that the 69, I don't remember the name, sorry. It's very different from all other Strad, but somehow it's closer to a Guarnieri of the future, telling us that maybe Guarnieri got inspired by the first Stradivarius. And from 79 onwards, you have like a big cluster with some subclusters till 1720, which, I mean, I just Googling Wikipedia, the golden period is considered from like the 1700, but already 20 years before they were similar. And interestingly, it's the distance between a violin from the 10 years different, it's much closer to a violin from the 1715 than to the 1669. We can do the same for the FRF. So check the next talk. And with this, like doing the same principal analysis component, instead of having a 10-dimensional diagram, we can put all this in an embedded dimension, it's called, where you have just the two principal components, and you have how the way Strad clusterized, Guarnieri, it's very different. One of our artificial intelligence violins is here, but we can put them anywhere in this plane. And nicely, we can move. This is very simple because the space is Euclidean. So the distance, the shortest distance between 2 points, it's always a straight line. So with a straight line in 10 dimensions, you can go from Guarnieri to Strad very easily. And have, I don't know, 3/4 Strad, 1/4 Guarnieri violins, and study how they're sound. Why this is interesting? Because the PCA and this simple like ruler and compass measurements are two ways of describing points. And I'm referring to violins as points in a multidimensional space. And this is what we call a coordinate transformation between one system of coordinates to another. You can describe this point as X, Y, Z, or as R, theta, phi. And whatever the name you put on the point, it's the same point. So as long as you have enough different dimensions and orthogonal enough, you can describe anything. And you can use that as a base for your prediction. And that's why what we want to do in the future is to use this simple measurements to predict the sound in a way that, I mean, this is the artificial intelligence is essentially a matrix multiplication. So you could add your own measurements of your mode, of your model, and have a prediction of the modes. Very accurate and without doing any FEM simulation. Okay, to finalize. I think PCA can be a tool for experimentation. Why? Because it tells, I mean, from simulation, it's very easy to vary everything, and it will tell us the directions where there is more variation explained. However, these directions of like how to make a violin, they will be very unintuitive, unintuitive. Sorry. And you have that this weird direction. It's like that's what the example of the weird bicycle is. A PCA just like give us something to do in a mathematical way that we have a lot of predictability, but we have no narrative for, which is a bit of a trade-off. You can predict how it's going to sound as long as you don't understand what you're doing. But I think it's very, very interesting. And that will be, I think we have some time for question. If you want to contact me, that's my non-institutional mail, but the one I read more often, and my Instagram. I said I was a millennial, so I have my Instagram there. Thanks a lot. Oh, Claudia is not there. I'm just gonna give you the word.
Hello?
Yeah.
Sebastian?
Andrew? Yes?
I have a question. Your solid model is beautiful, it's smooth, and it's beautiful in terms of Boolean operators for meshing in finite element method. No? How do you obtain this smooth inner surface without the steps involved in different things?
We do I call it somehow diffusion equation solution, like numerical way. When you want to solve the heat equation, for example, the easiest way is to just start with a configuration, then you take 2 points, you take the average between them, and you update many times. So that's what we do. We kind of diffuse the height, the thickness along the different areas, so they are smooth exponential transitions between them. We do the same for the outline also, because even if your scan is like pristine, you're gonna have errors, so you need to get rid of them. And we get rid of all those with this method.
Okay, because as you say, the tools are more beautiful than your results in this step. So are you thinking to publish all the algorithm to obtain this smooth surface?
We explain it in the paper, but which is submitted, but maybe it's a bit too. It's not detailed enough because we didn't want to go into the detail. But it's actually, I mean, it's 3 lines of code, and that's my favorite sentence with my student. And you just do a while loop to each of the points randomly, and then average around. We can talk about later.
Okay, thank you. Congratulations.
Thanks. Andrew is lowering with his hand raised.
So there are people who have raised their hands. If you don't use the presentation, Sebastian, you should stop sharing your screen.
Yes, sorry.
Yes, on the recording, it's nicer to see you than seeing the participants.
Yeah, perfect.
But don't hesitate to share again if there are questions about some specific slide. Okay, so Dmitry.
Yes, Sebastian, thank you very much for your presentation. So you have a very impressive and powerful analytical tool that, in my understanding, you used to optimize the Violin to achieve the 2.5 to 2.4 ratio between mode 5 to mode 2. And the ultimate goal of this kind of model, I would expect, and you said that, I guess, would be a system that can help you where you will put the Violin spectrum, for example, for desirable sound, and it will help you show how to construct the shells that will produce such kind of resonances. But exactly. You're not at this point yet.
No. We've been 11 months working on this, so I think we need a bit more time. But the idea is, I mean, actually you can go even a bit further, and like after the talk of Rafa and Mirko, I will explain that we see the violin as somehow a machine that converts design parameters into a sound sphere. And we strongly believe that you can go from the parameters to the sound and from the sound to the parameters. that will be the final goal.
Yeah, I guess so. Maybe it will make any sense to marry your soft with romance.
Yeah, I think we could do it. I mean, have a really fast collaboration. If they run as many simulations as we did, we could like train another neural network and see the other observables.
And at the point where you are now, when you can change thickness, arching, outline, if we have a given piece of wood with a given density, for example, can your data predict how to treat this piece of wood to get a plate with particular weight and particular modes? And if this piece of wood is suitable to get a particular modes and particular weight?
I mean, I would say yes, but we need to do some experiments first. And that's like also in the to-do list. And that's why we want to CNC stuff to like make simpler geometries first to see if the method works. Because here we're assuming that our FAM simulation, it's accurate once you define the model parameters. And we haven't validated that experimentally. So we don't know if we fit the parameters for one shape, it will be valid for other shapes. I mean, the idea is that yes, but anyway, we need experimental data.
Yep, thank you.
Haris? Haris wanted to ask a question.
Oh, Harry, yeah. The deformation of the corners. If you look at the presentation, I use the ribs because the ribs, they wear less. They are protected by the top and the bottom. So if I look at the tops, it's impossible. It doesn't work. And that's a problem that why we cannot do it with pictures, because the pictures are too deformed. You need the 3D scan of the ribs. That's the nice thing. And the deformations,
yes,
I mean, we don't compensate.
Sorry, may I add something to my question? Having seen a few scans myself, I was actually very amazed by the variability of deformation depending on each of the violins. I am assuming that based on the model, the deformation might be different. What exactly was the most important factor in deciding the distance between its point, its corner? Because we see the deformation in three-dimensional space, and from what I understand, the distance that you measure is two-dimensional, right?
It's 2D. Yes. Okay. To make it a bit technical answer, what we do is we select the plates, we select by hand just the ribs. So these are cloud point in 3D from where we take the principal components of like the eigenvectors of the inertia matrix. So the plate is aligned in 3D. It's never perfect. Then we project everything in the XY plane. We do some smoothing, the same smoothing I answered to Jesus. And we also average the points. So at the end, we have a lot of points and we take a Bezier curve that fits them all. So it's a 2D average of a 3D structure.
Okay.
And in this, and I mean, let me see if I find it. Just your question, I hear you when I look for something.
It's okay. I am mostly covered. I mean, it's probably the best approach that you can have given the data that you have to try to calculate the distances. I was wondering, since you mentioned a lot, the character of your research is somewhat of a prediction model. So you are trying to correlate distances to different modes and how a violin vibrates. So I was wondering if you don't have the distances of a violin and you only have how the violin vibrates, can you calculate the distances? For instance, having an idea of what the outline might be.
I mean, that's what we want to do, like that. I mean, but I don't know if you can just go directly the inverse way. I think it's ill-defined, but you can start from, like, if you have a base outline, that's something similar, how do you have to modify that so it gives the desired sound feel?
Okay, okay, I'm covered. Thank you very much.
Yeah, and here you can see the variations of the, for example, the three Guarnieris, and the green one, it's nicely because it simply was like very poorly repaired, so the rib is out of vertical. But since we take the average of these points, they somehow go away.
Okay, okay, I see. Thank you.
Welcome.
Sebastian?
Yes.
Okay, I have a question. Yeah, that's a great presentation. And I have a question regarding the parameters. So the profile and the height of the top and the bottom plate, that parameter were embedded in the polynomials, right? You have like a 4-order or 5-order polynomials. So that the coefficient or 6-order polynomial. So that's how you define the profiles of the plates, right? And so my question is, like, besides using polynomials, are there any other way to define the profiles of the plates?
I mean, we did it in two ways. First, for the thickness optimization, the longitudinal arching was defined as a collection of points. So these 100 points that you saw, like 100 by 3 coefficient, so it's 300 points. But since that's too complicated to keep, we just fit a 6-degree polynomial to the, but you can do pretty much whatever you want. But the idea is to have the minimum number of degrees of freedom. So the polynomial representation, it was a good compromise, even though it doesn't really fit the waist arching, but we can add another parameter there that it's like.
Yes, actually my point is the polynomials is good at like imitating the curves of the arching of the plates. But the thickness, the profile of the thickness, that's another like a really common the tuning parameters by the violin makers. So how do you put that into account? The
those are just like 8 numbers. The profile of the thickness, you just consider the like one thickness and you let the algorithm to create the interpolation. So you have 9 more parameters if you want to have a variable thickness arching.
Okay.
Variable thickness top.
Okay, so right now the polynomials you have is like you have like 4 cross sections, right? Like in the middle, in the top, in the bottom, you have like 3 cross sections, right?
No. I have 1 and infinite cross sections.
Okay.
Because I mean, we use 100. We have 100 at the moment for like, but it's the cross section are defined by the highest point and by the boundary conditions, and those are enough to solve because you have, I think, three variables, like A0, x squared, x fourth, yeah, 3. So you need 3 equations at 0, at one border, and the derivative of the border.
So that's translate into you have hundreds of polynomials you need to optimize in the network.
No, I have hundreds of polynomials, but they all have the same functional form. So,
okay, I see.
So I don't add them in.
Okay, yeah, I see what you mean. Yeah.
We can like have a more detailed discussion later.
Sure, sure. Okay, thanks.
Any other question?
I have another question. It's more like curiosity. When I see your project, I thinking all the time that you are simulating a top plate from an historical violin without, you cannot touch, and the top plate is attached to the ribs. This is not an disadvantage. It's only a curiosity.
I mean, we did it for several historical violins that are part of the museum collection, and I mean, I can do it for this also because we have the scan here, so it just takes half an hour. But I don't know. I think we just found the Messiah as like a nice referent for starting. Like it was an aesthetic decision.